And he holds several patents and has published a book chapter. Now, we are eagerly waiting for the presentation of Dr. S. Nitin Kale on.
Okay, so thank you everybody for giving me this opportunity to join this faculty development program. And thank you also for the kind words of introduction. So I'm Nitin Kale. I work with Nanosniff Technologies at IIT Bombay. So we are located at IIT Bombay. We are a startup incubated here. Today I'll be talking a little bit about Nanosniff, a little bit of introduction about nanotechnology, nanoscience, and then coming to the core MEMS area, we will discuss a little bit about the various MEMS sensors and actuators, a little bit of historical perspective, and then we get into the fabrication technology part of it. I'm sure there are a lot of mechanical engineers here, so a little bit on microfluidics. At Nanosniff, we are basically working on two types of MEMS devices. One is a micro cantilever, piezoresistive, and second is a micro heater, micro hot plate. So I'll be talking about those devices and maybe a little bit about their fabrication. We have developed an instrument for detecting explosives, so I'll also discuss about that. And another instrument to, or we have shown the proof of concept of detecting cardiac markers, so I shall be discussing about that. And finally, a couple of products, Omnicant, Sensimer, etc., which are essentially for laboratory use. So faculty who wish to, experiment with MEMS devices, in fact, write some project proposals, etc., also can have these instruments in their lab, do some experiments, and then they will be, confident of writing project proposals. So something like that. Okay. So as I said, we were incubated at IIT Bombay. We focus on basically nanotechnology, sensor-based products. We are good at sensor design, nanofabrication. We do a good amount of surface functionalization of the MEMS devices. A little bit on microfluidics. I won't say too much, but very little bit. We do handle a lot of biochemicals, and we have a good team which is into embedded systems. The instrumentation part of it. Look at designing the hardware, the software, embedded systems, etc. And of course, I have talked about our products. We have been funded by various government projects, investor money, and for a little bit of time by even loans as well. So that is about Nanosniff. So I know that a lot of participants here will have a mechanical background, mechanical engineering background. So there would be, and for even the others, it will be interesting to look at size issues, size aspects. So we can have a brief review of these prefixes: macro, meso, micro, and nano. So the objects that we see around the world very easily are macro scale. For example, buildings, bridges, automobiles, human beings, etc. There are certain objects or certain structures which we can handle with our own hands. So those form, or those are a part of the mesoscale structures. For example, grains, small insects, sand particles, etc. So these are mesoscale structures, typical dimensions in millimeters. Then we have the microscale structures, which we may or we may not be able to see with our naked eye. For example, bacteria, a lot of cells, dust particles, and I'll come to the example of human hair, which is about 100 microns in diameter. And finally, we are all aware actually of now the dimensions of viruses. So these are these are present in clusters, and they have a size of few hundred nanometers sometimes. For those who are with the electronics background, they are very well aware that today the MOSFET devices that we are able to fabricate are having a gate length of about 5 to 7 nanometers. Okay, so that's again a nanoscale technology. Many of the cell ingredients, for example, the proteins, the DNA, etc., also fall in the nanoscale regime. So this basically takes us from the nano to the macro. A little bit of physics. At the nanoscale, we observe that certain properties that these structures have, or these components at the nanoscale have, are quite different from what we see them on the meso or the macro scale. For example, we know Newton's laws of gravitation, that the force of gravity or attraction is proportional to the square, or to the product of the masses, and inversely proportional to the square of the distances, right? Similarly, we know Coulomb's law, which says that the electrostatic attraction or repulsion is proportional to the product of the charges, not masses, to the product of the charges, and inversely proportional to the square of the distance. Now, what happens is that if we start reducing the size, it will become apparent that because the density of the material is same, then because of size reduction, the mass is going to reduce. This will have an effect on the gravitational force between two objects, right? But the objects can still hold the same charge, even if their sizes are reduced. And therefore, at the smaller scales, at the real life scale with which we interact, it is more of the electrostatic or electromagnetic forces that are more dominant. Gravitational forces are not dominant at the scales we are talking about, particularly in the nanoscale. The second thing is that we are aware that at the nanoscale, for example, those who are using or those who are studying electronic devices know that the gate dielectric, the dielectric is an insulator, is now of the order, its thickness is of the order of about 1 or 1.5 nanometers. So what used to happen in the early 2000s, when silicon dioxide was being used as a gate material, since it has to insulate, right? So what used to happen is that the electrons or the charges used to tunnel from the gate into the substrate, because the thickness of the gate dielectric was very, very small. And that actually is a nanoscale phenomenon. So something that should behave as an insulator is now behaving practically as a conductor. So all the tunneling phenomena, for example, cannot be modeled with classical physics. So you have to bring in quantum mechanics, and that is how you can explain nanoscale phenomena. The third aspect is greater surface to volume ratio. So I will talk about this in a different slide. The fourth aspect is at nanoscale, random motion now becomes important because it can convey information. It can, at the local level, taking into account a little bit of thermal perturbations, it can actually reduce the entropy. Okay, that's possible. I'm not saying that it violates the law of thermodynamics, but very locally, you could have some very funny effects. And the last thing is, this particular slide, if you just follow my cursor, what I will say is that you will see certain vials all these vials are having gold nanoparticles suspended in them. So it's a colloidal solution. And you can see that the vials are having different colors. The solution is same. Therefore, it is the gold particles which are actually causing this funny effect. So what happens is that we know that we can see something because light falls on that object and then it reaches our eye. Right? And whatever is absorbed is going to be the color that we are going to see. What this picture is telling us is that we are seeing gold of different colors. So those particles that are suspended in that solution are absorbing the light of different wavelengths. How does this happen? This happens because the particle size of the gold nanoparticles is different in each of the solution, in each of the solvent. This tells us something very important. What it tells us is that you can tune the optical properties of a material by merely changing its particle size. And this is very important, and this is something that is exploited in the nanoscale regime. And since microsensors or MEMS is now moving from the microscale now into the nanoscale, it's important that we know this so that we can exploit this phenomena as well. Coming back to the impact of surface to volume ratio. So this is again a very famous slide. I'm sure you would have seen this. So just an attempt to revise it. So what you see is a block, a cube. It is having a certain volume. It is having a certain dimensions, and therefore it's having a certain volume and a certain surface area. Now, if this is divided into 8 parts, it is split across the middle, then what happens is that the volume still remains the same, but the surface area increases. This surface area increases because now you have exposed the inner surfaces. And if you go on dividing that particular cube, then you will realize that the volume still remains the same and the surface area goes on increasing, actually exponentially. So what this also tells us is, or it hints to us, that at small sizes, the surface is going to play a very dominant role. Okay, so that is the impact of surface to volume ratio. And this can be explained by various ways, or this can be seen in various natural phenomena. The best example is now people have understood that, which is the so-called lotus leaf effect, for example. One part of the lotus leaf is hydrophilic, the second part is hydrophobic. We can discuss that separately as well. But historically, nanotechnology is something that people have been using, although they may not be actually knowing it. For example, people have always used, in fact, Roman churches, for example, they have tinted glasses. And glass, as we know, is a supercooled liquid. They had some mechanism of mixing metal nanoparticles into the glass and keep it suspended so that you can change the optical property. But they did not, of course, know the basic physics behind it. The other example is the hair dye, for example, which is again some sort of a nanoparticle which is suspended in a colloidal solution. People say that Ayurveda, typically the bhasma preparations, for example, also uses nanoparticles. And what is important here is that the size aspect is very important here. So it is possible that at a certain size, a particular material can behave as a medicine, but at a certain particle size, it may be ineffective. And at a certain particle size, in fact, it may be toxic. So I'm just guessing, I'm just speculating, because the size of the particle definitely governs its behavior and the chemical interactions that it is going to have. Again, the mechanical engineering people will find a couple of things on this slide very simple. How does how do certain quantities scale with dimensions. But I will like you to focus on something that is present here. So we know that it scales, the volume is going to scale as L cube, etc. But for example, the frequency. So we know that the frequency is going to scale as 1 by L. So as you reduce the length, the resonant frequency is going to increase. And this has important connotations for using microsensors, for example, micro cantilevers as sensing devices when you are actually monitoring the resonant frequency. Another thing that you can see is, heat capacity, or in fact, heat flow is a good example. So as you reduce the size, heat is going to be exchanged very quickly, very rapidly. Another example is turbulence. So we know that in microscale diameter channels, the flow is not going to be turbulent unless you have a very, very high pressure. It is typically going to be a laminar flow. This actually becomes a problem as well. In terms of just small volumes, if you look at it, then if we know that, for example, the milk pouch that comes at our home holds about 1 liter of the liquid. That has a dimension of about 10 centimeters by 10 centimeters by 10 centimeters. Now, if you scale it down by a factor of 10, then you have 1 centimeter by 1 centimeter by 1 centimeter, and that is your 1 cubic centimeter, or what you call it as 1 milliliter as well. You scale it down further, 1 mm by 1 mm by 1 mm. Now that's a microliter. So you can see that it is cubically scaling down. The reason why this is important is that we are using, for example, our blood to do certain tests. If a certain test requires a couple of milliliters, which we know, which is the amount of blood that is drawn. However, if the same test using certain microscale sensors can be done with, by scaling it down, can be done with microliters, then it's a boon, right? For particularly the old patients for whom taking out the blood frequently every day is a big challenge, it can be a boon. So that is again a driving force that by scaling down, you can actually reduce the amount of chemicals and biochemicals that you require. In fact, the samples that you require to do the same test. So this is another driving force. Two quick examples. One is of an electric bulb, which has now practically vanished from the scene. We know that the filament inside the bulb is having a very small diameter. It's actually very light as well, the tungsten filament. Typically, it goes from room temperature to about 2500 degrees Celsius in about 20 to 40 milliseconds and cools down in about 50 to 60 milliseconds. This happens, because the thermal mass is very small. Okay. Now, at Nanosniff, the MEMS microheaters that we have developed and we are using for certain applications actually takes inspiration from this phenomenon. What it basically says is it's very difficult to maintain a temperature gradient. So across the entire filament, the temperature rises very fast, except at the edges. Those who are interested in the bio sciences, they will note that it is again very difficult normally to keep two materials apart in biosystems. So you need to have really physical barriers in the form of cell walls, which actually prevent two channels from mixing. Otherwise, it's again very hard to maintain a concentration gradient. Okay. Some more examples. Those of you who are interested in fracture kind of behavior know that even objects which are as strong as steel they tend to give away and fail. So why does this happen? One of the reasons, or one of the fundamental reasons, is that the material, which looks strong otherwise, if you look at its microstructure at the micro scale, you will find that it has a lot of micro cracks. And eventually, you have all those grains, etc., etc. And when structures fail, they are going to fail, or the failure is going to start across one of these cracks. So people use a lot of, thermal treatments to ensure that the cracks are minimized, the grain size is large, etc., etc. Again, another example from nature is, the lizard. So we are all aware that lizards find it very easy to climb walls. And if you look at the lizard, then it has very small or very weak arms. So it was always a wonder for scientists to really know, how do these lizards find it so easy to support their own weight and climb the walls. Then, of course, they did investigations. And they found out that the palm of the lizard has certain very, I would say, micro-scale structures. Biologically, it is called cilia. So this hair-like structures are there in quantities of billions. And what actually happens is that between the hair-like structure and between the wall, there are sort of weak forces, which are sort of hydrogen bond forces. Now, between one cilia and the surface, a hydrogen bond force is not going to be sufficient to hold the entire weight of the lizard. However, when you have billions of them, then the net force is definitely sufficient enough to hold the lizard. So again, this was a very interesting investigation done in the, I think, mid of 40s or early 50s, I believe. So they were Nature papers, etc. I will recommend you to actually read those papers. Now, what people have learned from this is that can you make structures like this? So people have made these structures similar to cilia. Okay. This is again by the technology of micromachining, and we are definitely going to discuss those technologies. What is the idea? The idea is that can you make a glue which is similar to the mechanism that the lizard uses while climbing the walls. If you look at that mechanism, then the lizard does not pick up anything from the wall. So its palm are always clean. Right? So if you can have a glue which is not going to pick up anything from the paper that you're going to stick, when you open up, then nothing like it. It's again $1 billion project. And some solutions very close to that have actually come in the market. So this is again a driving force. Okay. So now, till now, what I talked about was about nanoscience, nanotechnology, and how it is providing opportunities to engineers and scientists to make more innovative products so that people can use them and people can make their life easy. Something slightly different from this was a violin, which was micro-fabricated, I would say, at the University of Cornell. The strings have a diameter which is perhaps fractions of a micron. So they could actually make those strings and they could release it from the substrate. Release it from the substrate, by this I mean that this string is hanging and it's present only between this part and this part. It is stuck at these two edges. The violin may be fixed at the base, and it may be fixed here also in the bottom, one doesn't know. But the strings definitely are free. That is what you can see. So you can actually pluck the string and maybe you will hear a sound. Okay. From the point of an engineer, we know that we make a system with the help of materials, different materials. These materials go on to build components, again different components. And then these components go on to build different modules or subsystems. And eventually you have the entire system that you see. So that is how we engineer a system. Now, here I am trying to compare a system that has been engineered by humans and a system that has been engineered by the nature. And you will see a lot of similarity. There might be some differences, we can come to that. But the similarities are something like this, that if you look at top down, you have the system and you have the subsystems. For example, in this automobile, you will have the engine subsystem, you will have the transmission, then you have maybe the clutch part of it, then you have the braking part of it, instrumentation, etc. etc. Now, each subsystem then has components. Right? And then, for example, the nuts, the bolts, those are different components. And then each component is made up of different materials. Okay. And for example, people very well know that many of the tires that are coming in the market are made up of, or they will have a mixture of carbon nanoparticles inside them. That is to ensure certain properties of better thermal conductivity, heat dissipation, etc. etc. Okay. So this is an approach which explains how systems are engineered, and that is not too different from the greatest engineer, I would say, that is nature, that has helped the human body to evolve from very simple unicellular objects, or maybe certain chemicals in the form of certain proteins and maybe certain fats as well, in the very 4 or 4.1 billion years ago. So from those unicellular things, they replicated, they evolved, and finally you have a huge diverse ecosystem. So humans have, again, as a system, then subsystem, you have circulatory, you have nervous, you have digestive system. Then each system has its own organs. For example, you would have kidneys, you would have eyes, you would have ears, etc. Then these organs are made up of lots of tissues and cells, and then cells are made up of mitochondria, DNA, RNA, chromosomes, etc., etc. So even amino acids, proteins. So this is what is present at the nanoscale. However, one important difference, what I see typically as an engineer, is that most of the engineered systems tend towards modularity. So generally, components are modular. So one component tries to do one particular function, whereas in the systems that have been engineered by nature, generally it is not the case. Multiple or one component might be doing multiple tasks, and multiple components can interact with each other, feedback, feed forward kind of loops to do multiple tasks or to do a single task as well. So with this background, since MEMS has learned a lot from nature and from biology, because it has to interact with the real world, right? These microsensors and actuators actually have to react or respond or play or interact with the real world. Therefore, it's important to know the real world with which these devices are going to interact. So they have several names. Now more names definitely would have cropped up. For example, NEMS is the nano electromechanical systems. What it has, or why it is very important, this is a bit of an old slide. What it tells is that MEMS devices, sensors, actuators are present in various domains. For example, from aeronautics to automotive, telecom, etc. etc. Here is an example of a mobile phone where the microphone is a MEMS device, the earpiece is a MEMS device, the RF oscillators inside are MEMS devices. This thing that helps your screen to adjust when you tilt it, those are again MEMS devices. So MEMS, you can see that finds huge application in a simple product as well, and therefore it's a $1 billion industry today. It's also having it's coming in a big way in the healthcare sector as well. That is one area in which people can really grow. So in terms of fabrication, in terms of the fabrication technology, MEMS has borrowed a lot of things from the IC technology, the integrated circuit technology. For example, batch fabrication and miniaturization. So these are two important concepts that we talked about from the scaling aspect as well. So essentially, we are trying to integrate in a MEMS device some sort of sensing, some possibly actuation, it may or may not be, a way to compute and control from the instrumentation side, possibly communication, and possibly control the power as well. Here is an example of an accelerometer, which we again know is a very famous MEMS device. You can see that it has a lot of circuitry inside. It has maybe possibly those fingers somewhere inside, right? And some clocks, etc., etc. So this is the way you can actually engineer a MEMS chip. In terms of sizes, the MEMS devices today are, at least the suspended structure, the part of the MEMS device that is actually moving is of the order of, I would say, a few hundred microns to a few microns. Now, when I say size, I'm talking of the size which we use to machine. It is possible that we make the use of thin films, which are about 100 nanometers or so, but I will not get into that part of it because we are not machining something there. We are doing machining of a few tens of microns, a few microns kind of devices. And now people are going towards MEMS as well. So this is the scale aspect of it. People also talk of MEMS. The MEMS is the optical part of it. You put, you try to play with the light as well. The reason is that now your devices may have, for example, diffraction gratings or certain suspended parts, which can be made to move, and the wavelength of the light is very close to the dimensions of the moving part. So that's possible. Here is a very nice example of a work done by a PhD person for his thesis. So what this person had done is he had developed micro manipulators. So micro manipulators are are again components which are used to pick something and place something or make connections with something. Right? So what you can see here is that these people actually created a finger kind of a structure, which can be electrically controlled by applying certain voltages. But this finger kind of structure can be used to pick up cells. Now, this is the important part, right? So you can, because when you pick up something, if you look at the entire motion, how it happens, then you are essentially bringing the fingers together. You are trying to apply force to the object that you want to pick up, and then you want to place it somewhere. So you move your arm and then you release it. So all these things were possible with this particular structure that was developed. And this is a MEMS structure. So it can be used, for example, to analyze single cells. So if there is, for example, a tumor cell, then perhaps it can be extracted from the tissue, of course, by observing under a microscope. So you can see a lot of movement control is there, which is, for example, shown in this particular image. Okay, so one most popular application for MEMS has been the accelerometer. Now, in an accelerometer, what that accelerometer does basically is it senses the change in speed, and the change in speed can occur if the vehicle crashes onto something. So, if there is an acceleration, if there is a change in velocity, so it immediately halts or something like that. Now, it has a moving part, which sort of remains in motion or tries to remain in motion, and it senses that there has been a change. The velocity has changed or something has stopped. Because this moving part can now respond, then the moving part or whatever happens with the moving part, and it can be transduced into a capacitive change or a piezoresistive change, but that is picked up by the piezoresistive sensor inside because it's going to deform. This part is going to deform. And then if it's a capacitive, you can pick up a change in voltage. If it's piezoresistive, you can pick up a change in the resistance. Okay. I've talked about something, I've talked about bulk micromachined. So bulk micromachining is something that we are going to discuss very soon. About piezoresistive. So now I have a question. I will put the question. I'll just halt my talk for a moment and put a question. Are you aware of the concept of piezoresistance? Anyone from the audience may please respond.
Yes, sir.
Okay.
Can I answer, sir?
Yeah, sure.
Yes,
so
sir,
how do you define piezoresistance?
Sir, piezoresistive material is the material when we passes electricity, it gets contracted and elongated, and vice versa when it is subjected to compression and tension, it induces voltage. Sir,
I'm afraid that is piezoelectricity.
Yeah.
So that is not piezoresistivity.
Okay, sir.
Okay. So piezoresistivity. Anybody else?
Yeah, can I say something?
Sure.
Yeah. So this is Suhas Deshmukh, and I would like to tell you that piezoresistive means if you are going to apply a force, resistance will change. That's what these two words are clubbed. Piezo and resistance.
Yeah.
Is that okay?
Correct. Yeah. So we will go a little bit deeper into that. Hold on. So, what it says is that if you apply a force, the object is going to deform, and the electrical property, which is resistance of that object, is going to change, right? Mr. Suhas or Dr. Suhas, are we on the same page?
Yeah. Right. I got it.
Now the question is, why should it change?
Yeah, what it is?
Why should the resistance change?
Sir, may
if you deform it, why should the resistance change?
Sir, may
obviously there will be a somewhat molecular changes will happen which will oppose the flow of the electrons, and then resistance will create a change, I think.
Okay, we'll reach there one by one.
Yeah.
We'll reach there one by one. Yeah. So in between, anybody else who would like to answer?
Sir, the resistance of any material changes when the deformation change is occurred in that particular material. Due to that, the length and the cross-section area changes, so that the resistance changes.
Okay. So what you are saying is that R is equal to rho L by A, and this L by A, that is length by area, changes due to deformation, and therefore resistance changes, right?
Actually, connected to semiconducting materials, semiconducting bulk resistance. Semiconducting bulk resistances. Yes.
Yeah. So, anything else that you want to add to that?
You are perfectly correct, sir. Nothing else. It is only delta rho upon rho. That is the piezoresistivity factor. In case of
semiconductor. We have not come to the rho aspect yet. We are just talking of R is rho L by A. R is rho L by A. So I am just talking about L by A, which deforms.
Yes.
So I am coming to the rho part of it.
Yes, sir.
So this L by A change is very small. Okay. Yes, hardly, the gauge factors typically are, 1.5 or 1.6. Right. To enhance the gauge factor, as the other person rightly said, you have to play with the resistivity. So there has to be a delta rho. Okay, delta L by delta A or L by A, those changes are very small. So the thing is that we need to exploit delta rho. Now the question is, why should a change in resistivity happen because of deformation? Have I?
Sir, in nano level or the micro level structures, whenever the compression or tensile force is applied, the crystal structure of the material will be changing. So by that way, the resistivity will also be changed.
Why? Why should it change?
Because the resistivity comes with the crystalline structure of any material. So that whenever the compression or
No, but see what can happen is, see, if you are going to change the crystal structure, first thing is you are going to need a huge amount of force.
Yes, sir.
Okay, this is first part. Second part is that instead of behaving like a, I will just put it in a different way. So you will get into an irreversible change. So that is now not how piezoresistivity will work, right? If you change the crystalline thing, it's going to behave in a absolutely different manner, and that will be an irreversible change. Okay.
Yes, sir.
So anything else? Yeah. So anything else? Any other idea behind that? So, rho is changing, right? And we have not changed the material. What we have done is we have applied some force, strained the device, and the rho has changed. Okay. So recall that rho depends on what? Rho is the resistivity. It depends on the carrier concentration and the mobility, right? I recall your, maybe second year engineering semiconductor physics, or maybe something that you would have done in maybe 12th or so. Anybody?
Yes, sir.
Hello?
When the mobility changes, the resistivity changes because the conductivity.
So what we are saying is, so what we are saying is that the resistivity depends on mobility and carrier concentration. So obviously, because of straining, the mobility and carrier concentration should change.
Excuse me, sir. I have another one question. When the carrier concentration changes, means the carrier concentration can be engineered only in semiconductors. Am I right, sir?
Yeah. But I'm coming to all those things. See,
okay.
I'm coming to that. So just hang on with me that the resistivity depends on carrier concentration and the mobility. So if resistivity is changing, it means that these two things, or at least one of them, is changing. Okay. Now, if you look further deeper, then carrier concentration and mobility both depend on a property of the charge carrier, which is called as the effective mass. So it could be the effective mass of the electron, or it could be the effective mass of the hole. Right? So this conductivity or resistivity depends on carrier concentration and mobility, and both of these things are actually depending on the effective mass of the carrier, of the charge carrier. Now I'll take you further into the physics of it. What actually happens is that now this is into the band theory part of it. So because of straining, there is a change in the electron band structure. Okay. And because of that, what happens is that certain holes can go from conduction band to valence band, or from a valence band to charge carriers. They can go from valence band to conduction band, or they can fall from conduction band to valence band. So that effectively tells you that mobility and carrier concentration can change. Okay, and this happens because of strain. So if you look at those EK diagrams in certain literature, it will become clear. Now let us go backwards. So strain changes the EK diagram. Change in EK diagram changes the effective mass. Change in effective mass changes mobility and or carrier concentration. And mobility, carrier concentration, if both change, then your resistivity changes. And if your resistivity changes, then your resistance changes. So this is the complete link that I wanted to kind of expose in front of you. Is that clear?
I have a question, sir.
Yes.
Yeah, the question is when the material is being deformed, so you said that the electron band is going to change so that the electrons in valence
The
band.
EK diagrams will help in understanding that.
Yes, sir. When the electrons in valence band comes to conduction band, or the conduction band electrons may go to valence band. So how we can say that the conduction electrons are going to increase by the manner?
So I'm not actually getting into that part of the physics. What I would suggest is that if you look at the EK diagrams, what it essentially says is that your your effective mass is going to change. So I'm not going in the direction of what we say as flow of electrons, etc. I'm not going in that direction. What I'm talking of is the effective mass of the charge carrier. Okay, we have not applied any voltage, by the way.
Okay, sir.
Okay. So this was something that I wanted to explain, that there is a little bit of physics behind piezoresistivity, and I hope you will find it interesting. Okay. So after accelerometers, people wanted to check, if they can make motors, micro scale motors, and people struggled to make two particular, I would say, MEMS structures. Again, mechanical engineers will know sort of a revolute joint and sort of a sliding joint. So that made it possible for, again, objects to move very easily in a controlled fashion. And this could be now, batch fabricated. So that how that is done, we'll come to the next slide. And before that, MEMS devices have come into the industry for a variety of applications. For example, pressure sensors, inkjet printers, micro mirrors. So these are three examples that we shall be seeing, but a lot of other MEMS devices as well. And historically, since 1970s, I would say. So as we have seen, in a MEMS device, you would have some sort of a suspended structure, which could be a beam or a diaphragm or a cantilever. It will be connected to some sort of a substrate, and there would be some electrical, optical components on the device. They are small, of course, because you want to, make them or you want to exploit the nanoscale features, of course. And making in large volumes, you can make them cost effective as well. Here is an example of a pressure sensor. And from this example, I'm trying to explain the importance of packaging. I'll just hold on for a minute. I will mute myself. I'll just have a little bit of water and come back. Please, about 30 seconds. Yeah, so what you see here is a pressure sensor. The MEMS device is only this part. Can you see the cursor, please?
Yes, sir.
Yes, sir.
Okay. So this is the MEMS part, and this is the suspended membrane. Okay. This is the wire which is connecting the MEMS device with some sort of a PCB, and then this PCB is going to interact with the device actually interface the device with the outer world. Whatever you see outside, other than the MEMS device, is actually the packaging part. So this is the packaging part. There is some jelly filled inside, some gel, right? What this should be telling you is that, packaging is a very important aspect of MEMS. And there are, separate departments nowadays which deal with packaging. Packaging is important to protect the MEMS device, do a lot of thermal management. It is also helping in calibrating and testing the devices. What is important is,
Excuse me, sir.
50. Yes.
Sir, the screen has gone blank. The PPT is not visible, sir.
Okay.
Sir, thank you, sir.
Hold on.
No, PPT is visible, sir. It's visible, sir. It's visible.
It's visible.
It is visible, sir. No doubt, sir. Everything is
Maybe then it's okay, right? Full screen is there, right?
Yes.
Okay, maybe with local.
Yes, it is visible. Yeah, you pin those who are not like getting the PPT. You can pin the presentation of Dr. Nitin Kale, sir. So then it will be visible. It is visible, sir. No problem.
Okay.
Sir, it is visible. No doubt, sir.
Yeah, thank you. So what you see here is, or what I would like to tell particularly the faculty members is that, about half of the solution to a problem is in packaging, and the rest half is in the MEMS device. So packaging is equally important, right? And when you talk of packaging, then lots of materials are there and lots of processes are there which are used to package a device. So that could be another area in which you can think of doing your research. Okay, here is an example of a digital micromirror, essentially for light projection. This device is called a DMT, digital micromirror device. It was invented by Texas Instruments, and they made a lot of money on using this device. Essentially, it is used to project light on the screen, and of course control, which pixel should light up and which pixel should be silent or dark. So what you see here is, this is an array of micromirrors. Okay. And what these micromirrors have essentially is a mirror that can be tilted, some sort of beams and some sort of electrodes where you are going to apply a voltage so that you can tilt the beams. Now what happens is, structurally, you have a reflective surface, you have a hinge, we know what hinges are, and then we have electrodes. Right? So by addressing a particular mirror using these electrodes, applying voltage high or low to this, you can make the hinges to tilt, and of course you can decide whether light falls at a particular place or not. So this is the device, and it has made a lot of money. Another device, I'll now come to the piezoelectric part of it. So as somebody had rightly said, that if you apply a voltage, it deforms. If you remove the voltage, it will come back to its original shape. So that particular thing is exploited in the inkjet printer head. So what happens is that you have a piezoelectric element, and you have a reservoir of ink here, and you have a nozzle here. By applying a voltage, you can pull this particular element. So now more ink can actually get inside the chamber. And when you want to release the drop, you can remove the voltage so that the drop is going to be pushed out. So it's as simple as that. It appears very simple, but the piezoelectric element makes this possible. The other technology which is very popular in inkjet printer heads is use of a thermal inkjet print. What it does is that you have some sort of a micro heater. Again, you have a nozzle, you have a reservoir. What you can do is, if you heat it, there would be air inside the liquid. So the air is going to expand, a sort of a bubble is going to form. The liquid is going to be ejected out. Right? And when you of course cool it, then you can draw, because now the volume has reduced, you can draw liquid into the chamber from which you want to further eject it. Now these are two technologies, the piezoelectric and the microheater or the thermal one. These are used by, one is used by Epson, one is used by HP. Now which is using what, I don't exactly recall, but both have been very successful. And today HP and Epson, they are actually looking for applications where these technologies can be used, because nowadays people don't mostly use inkjet printers, but the technology is available. So they want to find out different applications for this. Now coming to the physics part of it for an inkjet printer, you can see now I'm just going back from engineering to the science part of it or the physics part of it. So as mechanical engineers, you know that it depends, that motion of the drop depends on so many things, right? What is the disturbance? What is the density of the fluid? What is the surface tension? At what temperature the entire ambient is there? At what length is the drop going to form? From the liquid, stream of liquid, it's going to get converted into drops. What is going to be the spacing between the drops, right? What is going to be the diameter of the drop? So all those things have to be thought about. And knowledge from physics actually helps in doing the engineering part of it. One very simple thing, if the drop is moving, it's going to encounter viscous forces from the air. It's going to possibly feel a little bit of gravitational field as well, although the viscous force might be much more powerful than that. But you have to think about it. That is what I was trying to bring about from this slide. Okay, we'll just skip this slide, no problem. Now, of course, this upper part of it says that you can, by using electric field, you can deflect the drops. I'll not get into that. What is important is on this slide, or on this part of the slide. What this shows is a MOSFET sort of a device, a transistor, which can be switched on and off, and therefore which can control whether ink can be ejected using either that piezoelectric method or the thermal method from this nozzle. Okay, so what is now happening is that there is a marriage of the CMOS technology, the technology that is used for making your chips and the memories of your laptops, with the MEMS. So you have a MEMS device, sort of a nozzle which juts out liquid, which is on top of a CMOS device or a logic device. Okay. Further delving into engineering, what are MEMS devices made up of? And we'll now talk about materials and processes. In the early 70s, and in fact, recall my earlier remark that MEMS devices or the MEMS technology has always followed the CMOS technology. Therefore, whatever CMOS or equipment was used to fabricate CMOS devices, that same equipment, when it became outdated, for example, people moved from, let us say, 90 nanometers to 65 nanometers technology. Then the 90 nanometer equipment might become obsolete, or from 65 to then 32 and then to 5 meters, etc. 5 nanometers technology. These equipment become obsolete, and the MEMS people, they are like vultures. So the moment something is, or scavengers, I would say, not vultures. The moment CMOS industry, treats something as obsolete or discard something, MEMS people are there to scavenge, to take those equipment, to take their processes as well. Okay, let's try to understand this. It's not just the equipment that they are preying upon; it's also the process and the process recipes that they are going to take or they are going to use. So keeping that in background, if you look at this slide, Phase 1 started with old materials and old processes. Now, what those old materials are? For example, silicon, silicon dioxide, silicon nitride, simple lithography, CVD techniques, etching and doping techniques. So these are old materials and old processes. The next phase came with new processes came in. The materials were the same, but the processes were new. So, for example, different micro machining methods, sacrificial layer processes. We'll discuss about this. Deep RIE, wafer bonding. We'll also discuss about wafer bonding. So these are new processes. Then there was another phase where you used these new materials and the old processes. Okay, so for example, people used ceramics, people used PDMS and used the old process of lithography. So PDMS is a new material, but lithography is an old process. Or silicon carbide, that's again a new material, a very popular material for harsh environments. And today, in fact, for the last, I would say 8 to 10 years, people have been using exotic materials and exotic processes. I'll not get into that, but for example, thermal embossing. Okay, so some sort of embossing technique, it was never there in the past. And for thermal embossing, you use some sort of plastics as materials. So that is new material and a new process. Okay, so is this slide visible?
Yes, sir.
Okay. Now this is a clean room. Have you visited clean rooms? Semiconductor clean rooms?
Yes, sir.
Okay, many of you would have, or some of you wouldn't have. That's okay. In a clean room, where semiconductor devices, MEMS devices are fabricated, 3 important parameters have to be controlled. The particle count should be low. The temperature has to be controlled in a certain band, and the humidity has to be controlled. There is separate lighting. What you can see, this person, for example, is wearing a bunny suit. So you have to have a certain attire, certain clothing. You can see a person here, a person here, a person here as well. Now, since we have this COVID situation, we now know, the hood, the gown, the footwear, etc., etc., which you would have seen people wearing in the hospitals. Okay, it was not very popularly known, I would say, but now everybody knows what the attire is. What you should realize is that the typical hospital scenario, in fact, even the ICUs, will have a particle count, or the class as we call them. So it will be a class 10,000 kind of a clean room. Now 10,000 kind of a clean room means that you could have 10,000 particles in 1 cubic foot of space, and the particle size will be about 0.5 microns. Each particle size will be 0.5 microns. So that is the spec of a class 10,000 clean room. 10,000 particles of particle size less than 0.5 micron in 1 cubic foot of space. If you compare that with semiconductor clean rooms, then at IIT Bombay, for example, they have a class 1000 clean room. They have a small part of it is also class 100. In places like Intel, you would have a class 10 and a class 1 clean room. Okay, so class 1 will be 1 particle in 1 cubic foot of space, having size of less than half a micron. So that kind of criteria has to be met, and this is all met by proper particle count, temperature, humidity. It's maintained by proper HVAC, So you can see how HVAC is very important. This is again a mechanical engineering specialization. Ventilation, you will have blowers with very high airflow rates, so that the air is changed, something like 100 times per hour or even more, as you want more clean rooms. And then you have air cooled, so you have the temperature control. You have some sort of desiccants, so you can control the humidity as well. Is that part clear? Any questions on that?
No, sir.
Okay.
No, sir.
Okay. Okay.
No, sir.
Now I move to the first element of fabrication. So we start with making the silicon crystal boule. How this is made is that you have silica, the sand from beaches, that is melted, high temperatures, remove oxygen, remove lots of impurities, sort of refining process, so that you have molten silicon. And molten silicon is, mechanical grade silicon. Further removal of impurities is going to give you basically a molten bath or a molten fluid of silicon, which is reasonably, or which is high pure, I would say. It will be close to 99.99 kind of % pure. Okay, now what happens is that it's molten. So it's at about, let's say, 1500, 1600 degrees Celsius. And you do what is called as a crystal growth process, wherein you have a base crystal that is inserted into the molten bath, and it is rotated. And as you rotate it, it is slowly drawn out. Now, since when you draw it out, the temperature is less, the melt is going to solidify. And the melt is, when it solidifies, it's going to solidify as per the layout of the crystal, or as per the orientation of the crystal. Because, you have, again, thermodynamics issues. That's the, minimum energy level, okay, at which it's going to have the minimum energy. So it solidifies slowly into a single crystal. And as you draw out, you can have a huge bowl. The length of these bowls could be 2 meters, so more than a person's height of 6 feet, 6.5 feet kind of bowl lengths are there. The diameter of the bowl could be starting from 2 inches. It could be 12 inches as well today, for example. These bowls are then diced, I would say sliced into wafers, and these wafers are polished. The polishing is so good that you can actually see your face in that if you look at a wafer. Maybe if you visit IIT Bombay sometime or visit Nanosniff sometime, I'd like to show you physically how a wafer looks like. So you can have lots of these wafers cut, and now these wafers are there available for processing, for the MEMS or the CMOS processing. Before getting into the actual processing, let me give an example of a pizza. So this wafer is not different from the base of a pizza. Okay. Only thing is that, the pizza base is about maybe 0.5 centimeter to 1 centimeter thick. And the thickness of this wafer could be less than 1 millimeter. For a 12-inch wafer, I think it's about 1 millimeter these days. For the 2-inch and 4-inch wafers, it's about 0.5 millimeter to about 300 microns or 0.3 mm. So whatever happens, then taking the pizza example, is you would have toppings on the pizza base, and you would have layers upon layers, for example, of cheese, maybe some condiments, some masalas, some butter, etc., etc. Maybe sauces at a later stage. So those are depositions. So those are new materials that are adding onto the base. So you can keep that example in mind. The first method, the first semiconductor process that I like to talk about is oxidation. Oxidation of silicon happens even at room temperature, but the oxide that grows is not of good quality, lots of defects, and it grows to about 2 nanometers at max. To really grow a good quality oxide, you need a furnace whose temperature goes to something like 1000 degrees, etc. Plus, there are two methods of oxidation: wet and dry. In dry oxidation, you don't use hydrogen. In wet oxidation, you essentially use hydrogen, and at high temperature, you create water vapor. And that's how. Okay, one important thing is, as you increase the temperature, the oxygen molecules tend to go deeper and deeper inside the silicon wafer. So that's a growth process. So silicon is getting converted into silicon dioxide. Okay, so that's important here. That there is a chemical reaction between the silicon and oxygen. And the higher the temperature, the deeper the silicon can grow. The oxide can grow, go inside the silicon. What is important is that silicon is getting consumed in the process of oxidation. So that is why it is called as a growth process. And this is different from deposition. I'll come to deposition very soon. An equivalent process is diffusion. Somebody talked about, doping, I believe. Right? There was a hint of that. So you need to dope semiconductors. You need to dope them because you want to change the electrical properties, the conductivity, for example. Now, how do you dope? So, if you have this as your silicon, please follow the cursor. If you have this as your silicon, and if you want to dope in this region, then you would put a hard mask on silicon, let's say up to this region, and the same hard mask up to this region. What you have basically done is you have opened the mask here. Okay. And now you put a source of dopant here. It could be another wafer of, let's say, boron. Okay. So there is a silicon wafer and there is a mask. The mask could be reasonably thick oxide or nitride. And you have an opening in the mask. You raise the temperature, you put it in a furnace, you raise the temperature. Now these dopants are going to diffuse. Boron has a very high diffusivity, so it's going to diffuse. And you will have a profile of boron in the silicon, which is something like this. And the rest is something that you would be knowing that, boron and silicon form bond, and it would leave a hole behind, and now that becomes a conduction, it now becomes a charge carrier. Okay. Any questions on this diffusion? So why should something diffuse?
In order to get a P-type or N-type semiconductors.
No. That is, why do we carry out diffusion? That's not my question. My question is, why do things diffuse into one another? Why does diffusion happen?
Due to the high temperature, the reaction between the silicon and the other dopant materials due to the valency in the outer shells of the silicon, so that the diffusion process takes place.
No. Well, there are a lot of things that you have spoken about.
Hello.
I would suggest everybody to think about, why should diffusion happen?
Hello.
It's such a fundamental process. Yeah.
Sir, because of concentration gradient?
Yeah, concentration. But then the question still remains, why should diffusion happen? Concentration gradient की वजह से diffusion होता है. But why? See, it's random motion, right?
Yes, sir.
It's random motion, thermal temperature, high temperature, right? Allows random motion. So if you have a gradient, more is going to flow from, wherever it's more to wherever it is less.
High concentration, yes, sir.
Yeah, from high to low. And it is basically obeying the law of, entropy, the second law of thermodynamics. That's what it's obeying, that's all. If you reduce the temperature to absolute zero, right, then diffusion is not going to happen because there is no random motion. So we don't care about temperature gradient. But the moment it is even a slight degree above absolute zero, the law of thermodynamics is going to kick in. Okay. So we'll skip. The other technique, so growth is one technique of, kind of making a film on silicon. The other technique is thin film deposition. And I'll be specifically talking about chemical and physical vapor deposition. Please remember that deposition and growth are two different things. In growth, the substrate is consumed. In deposition, the substrate is not consumed. The film is simply added. जैसे आप bread के ऊपर butter लगाते हैं, right? So you have a thin layer of butter on the bread, or you put a slice of cheese on the bread, then it's basically deposition. Okay, silicon dioxide is, silicon is getting, some part of silicon is getting converted into silicon dioxide. So the thickness of the actual silicon is going to reduce. Please remember that the substrate gets consumed in a growth process. This doesn't happen in a deposition process. So basically in a chemical vapor deposition, what do? You have again some sort of a reactor on which you put in source gases. For, let's say you want to deposit silicon nitride. Then the source for silicon nitride would be silane, SiH4, and ammonia, that is NH3. Right? And what you do is at high temperature, there would be thermal energy, some sort of dissociation, and you have silicon and nitrogen combining. And then they form sort of molecules of silicon nitride, which go on and coalesce and nucleate on the substrate, and then coalesce as well. So that's how deposition happens. There are two types of depositions: reaction rate limited and mass transport limited. Basically, mass transport will mean how much gases you are putting in, the quantity of them, the flow rate of them, and the deposition being a function of that. In reaction rate, it's the temperature. At high temperature, you would have higher deposition rate. So those two regimes are there. This is an example of a chamber which is doing deposition at atmospheric pressure. Atmospheric pressure. So you would have, gas cylinders somewhere here, which are going to give those gases or vapors. These are mass flow controllers. And then you have some sort of a heating element around the tube, the reaction chamber. And then you will have some sort of an exhaust for this. Okay. In low pressure CVD, which is the popular technique today, in addition to all what you saw here, you will have a vacuum pump. So this vacuum pump essentially evacuates the chamber, and then the gases, of course, are removed. But the deposition happens at a low temperature. The quality of deposition is good. There is another technique which is called as plasma enhanced chemical vapor deposition. In this technique, instead of using temperature to dissociate the gases, we use plasma. That's all. So you will have two plates, a high voltage across it, RF or DC, depending on what you want to deposit. And then you can create a plasma, and let's say of using ammonia you get nitrogen, using silane you get silicon, and both are going to react, combine and form silicon nitride, and that's going to be deposited on the wafer. It will get deposited elsewhere also, but it deposits on the wafer as well. The advantage is you can do depositions at low temperature. The substrate temperature could be as low as 150 to 200 degrees Celsius. In LPCVD, you need something like 650 degrees Celsius. And I'll come back to this topic when we discuss about hot wire CVD. You can also do what is called as physical vapor deposition. One example is evaporation. The best example of evaporation is, I talked about light bulb. So let's go further back, the lanterns that we had. So you had a wick immersed in oil and you lit it up and you had a glass covering around that, right? So that was giving out light. But if you cover the open side of it, at the top, if you cover it with a cloth or with a paper, then of course in a few minutes, the light will go off. But on the paper, you will collect those sort of a black powder. So that's a deposition, okay, of carbon onto that particular paper. The same thing happens in a thermal evaporation setup. What you do is you put a charge inside some sort of a boat, and you have wafers which are lying around here, and you pass a very high current through it. The item that is present in the charge, it could be aluminum or gold or something. Of course, this is also evacuated. Please keep that in mind. So that is evaporated. And when it evaporates, it deposits everywhere, but it deposits on the wafers that are kept here as well. You can also do a E-beam evaporation. Essentially, you have an electron beam now generated by thermionic emission, and you control its path so that it falls onto this wafer, onto this boat on which the charge is kept, and the charge is going to get evaporated because of the high temperature. And of course, then you can control where, for example, it's going to deposit. There is another method called as sputtering. This is again a very popular method. It uses magnetron. It's called sometimes, in some cases, you may have a reactive sputtering as well. But the technique is slightly different. So you have a wafer here on which you want to sputter a material, let's say gold. Okay. You have a plasma chamber, so you have all those plates and high voltages, but you also have a sputter target, okay? And then you have a sputtering gas. So this sputtering gas is accelerated. First of all, it's ionized, so you have all those ions. Then those ions are accelerated so that they can hit the target. On the target, as I said, you have the gold target is there. So when it hits the target, the gold atoms are going to be sputtered, removed from the target. And they go everywhere, but they will also fall on the wafer. And therefore, this deposition is going to happen. Now, this gives very good quality of films. The adhesion is good, for example. The uniformity is very good. And it's very popular. Okay, so I will use this a couple of slides more, and then maybe we can break for about 30 minutes. So that we can join at about 11:30. In lithography is used to do pattern transfer. Deposition and growth are additive processes. Lithography is used to define something. So how that is done? So essentially you coat the wafer with a photoresist. Photoresist is a chemical that is sensitive to light. You selectively remove the resist from certain parts so that a certain pattern is going to emerge, and then do what is called as development. So first expose the resist to light selectively and then do the development. It's similar to the development which used to be done by the photographers earlier when those films were there. And then you always, of course, have an option to etch. You put some chemical so that the thing that you wanted to remove is going to remove, and then you can strip the photoresist. So this is a picture of a mask. Some dark areas are there, so light is not going to pass through that. Some bright areas are there, light is going to pass through that. Now, when you pass light through the mask and you expose the photoresist, you will form a pattern something like this. You can develop, and the photoresist from here will get removed. Now, this is the layer that you want to etch. So this layer will have an access to the etch chemical through this opening. Now, if you immerse it in a chemical which is having that etchant, then something from here, this particular layer in this region is going to get removed, right? And then you will have a pattern formation. After the etching is done, you simply strip away the photoresist by putting it in some chemical such as acetone. We'll just go through this. Resists are of two types, positive and negative photoresists. Positive photoresist typically will weaken if you expose it to light. Negative photoresist will harden if you expose it to light. So either of the two, by using both of the techniques, you can protect whatever part you want. So you may have what is called as a subtractive or an additive pattern transfer. For example, let's say this is the substrate, this is the mask. This is the film. You put a mask here, you etch. So when you etch, the film is protected here. So after you remove the mask, you have a pattern which is something like this. Okay, you may have a different sort of additive pattern transfer. This is your substrate. This is your mask. You do a lithography so that you remove the photoresist from this part. Now you deposit a film. Okay, and then you, this is called a lift-off process. So now you deposit the film and then you do the lift-off in which the photoresist is removed. So along with the photoresist, the film also goes from here and you have the pattern that you wanted on the silicon wafer. So these are two different techniques. This is not very popular in the industry, but it is very popular with the students. This is the thing that is used in the industry. It gives very good quality of adhesion and good quality of materials. I think we can stop here. Professor Bhole?
Yes, sir. Yes, sir. It's 11. So we will take half an hour break and then we'll join at 11:30.
Okay, fine.
Yes, sir. Okay.
Okay, thank you. Yeah.
The participants, we will have a break of 30 minutes, but do join at 11:15 so that so as to avoid the last minute rush. So we will have a break and the session will start at 11:30 sharp.
Okay, thank you.
And the feedback link after the schedule session, sir?
Yeah, we will, for the sessions, we will have the feedback and that will be shared in chat box.
This session or next session, sir?
It will be one feedback link only for the two sessions, okay?
कोई बात नहीं. बिंदू आवरा लवकर.